Okay, welcome to lecture 22. We'll continue our discussion on polar codes and hopefully complete the analysis of to show that polar codes achieve capacity with the and with block lengths which are polynomial in how close you are to capacity, block lengths and running time. Okay, so let's recap from last time. Recap polar codes discussion from last time. There were some main takeaway points. The first of them was the fact that what we wanted to do is come up with this code which comes close to capacity, as we need kinematic, but we said that the equivalent problem is actually work with linear compression. So we will work with actually linear, it's sufficient to come up with a linear compression scheme. Which H is mapping 0, 1, M string to 0, 1, M. The linear compression stream is for Bernoulli P. And then distribution of that. So we forgot about encoding and all that. But this, and we wanted M to be as close as possible to HPN is the best that one can do. And I want to be a little off. That's of course we want to come. And that's this epsilon is going to govern various other parameters. Question is, we're going to come up with some code that has this. How large n should be so that it happens? We want n to be polynomial. So what are the things we want? We want a decompressor. I'm just to have a decompressor. D such that probability when you pick a z from Bernoulli Pn and you feed d of hz, the probability that you don't get this is really small. This is one or this is what we want to go exponentially small. Then, and we also want these pictures, that is, we want n and the running times of the decompressor to be all in polynomial. Not little one, I want it to be a very small function of. I want it to be a very small function of epsilon. Let's keep it epsilon. So we have only one parameter epsilon, which is how close we want to capacity, and we want all of it. We want n not to be too large. We want n to be in polynomial 1 over epsilon 1 basis. On the running time of the decompressor to be in poly 1 over epsilon, and we want this error to be in epsilon. This is what we want. We can do this. We can. So this was the first of the things that we had said. We reduce it to this problem, and then having said that this is the problem we want to do, we talked about something called a polarizing matrix. We said that if a matrix, what's the polarizing matrix? Matrix P is an invertible matrix. And we had defined, we had made two definitions. We first defined as tau to be a set of coordinates I and n, such that and P is a matrix, and we're going to call W is equal to P, where Z is. So Z will always refer to the Bernoulli Pn distribution. W is the image of this one. We wanted the number of guys for which these are unpredictable groups. So even given the path, sorry, not less than or equal to 9. Less than 9. So S tau basically is the set of unpredictable groups. We defined this S tau, and we wanted to show, and we had this notion of the matrix is epsilon tau polarizing Like, how did I define this last time? If basically if the size of S tau is what we want. I think this is exactly HP plus epsilon. So that's if a matrix of polarizing if it has this picture, and we wanted to come up with this. It said that if this was the case, if we manage to lay our hands on a polarizing matrix, then what's the code? The compression scheme is just apply P on the input and then output P only restricted to S tau. That would give you the compression scheme. And we also say, given this is a very natural decompression. Decompressor is also the most natural thing. And both these work perfectly well. So the question now came to, and the error was also, notice what was the error? We'll look at the error a little more. The error was basically tau times n. So each time the unpredictability was tau. Tau here is the entropy, but we then had a proposition stating that if the entropy is related to the, well, if the entropy is very low, then the probability that it's not the most likely value is also at most tau. Therefore, for each of those, for each of the predictable bits, the error will be at most tau. Therefore, total error will be tau n. So we get that if we had a polarizing matrix, then if we had a polarizing matrix and we restrict our attention, we have this compression scheme which takes applies P and restricts it as tau, then we get a thing in which the error is just tau times n. Now notice this tau times n is what we want it to be this small epsilon. This is the error over here. So we want tau. So what I want you to keep in mind is this tau that we want over here, how this one should be a really tiny number because it's going to get multiplied by n in our error analysis eventually. So tau is a number that I really want to go to 0, but not just it should go faster than 1 over n. So ideally, I would like it to go like 1 over n square or 1 over n cube. This is what I want, and keep this in mind. This will be important later on. Tau is something. Whereas tau is something. Yeah, let's keep that in mind for now. And so this was the notion of polarizing S tau. This was the important definition. And
it's polarizing.
Huh?
Is epsilon for polarizing?
What did I write here? Yeah. Now, third was finally Arikan's construction. The explicit construction. And the construction was, let's ask for the most simple case what the construction should be for T2. It is taking 2 bits. So then T2 is going to map 0, 1, 2 to 0, 1, 2. And there's basically only one construction that we can think of in this. If you have U and V bits, it goes to U plus V. That's basically, if you don't want, because the only other constructions, U going to U or V going to V, or the other way around, and none of them will, you need some mixing to happening. And we'll come to this later. What is going to happen eventually? So this is say unpredictable bit with probability, say it's coming from Bernoulli P. And this is U and V are independently coming from Bernoulli P. Then U plus V is going to come from a much it's going to be like Bernoulli 2P problem. And P is very small, it's going to be more like 2P. Therefore, the entropy here is going to be much higher than the entropy of this. And because some of the entropies of these should be equal to some of the entropies of this, the entropy of this conditional on this is lower than the entropy of this. So one is increasing, one is decreasing, and this is what we want. We want to apply a set of things in which a whole bunch of guys are going to go to 1 and a whole bunch of guys are going to go to 0. The guys which are all going to 1 is where we are going to put the compression scheme on. The rest all you're going to eliminate because there's hardly any randomness in it. Those are all fixed bits. Given the past, you can know how to predict it. That was P2, and then P2n, more general of UV. UV are vectors here, was defined recursively as Pn of U plus V. and Pn of these. We have the recursive definition and pictorially before we had 4 things, say A, B, C, D. What is going to happen is the following. Getting at next A and C first, B and D first. So I get A plus P, B plus D, C, D, then I mix these two, I get A plus P plus C plus D, B plus D, C plus D. So the output, so if I start with 4 independent Bernoulli bits, the output bits are going to be A plus B plus C plus D, this one. And somehow we need to show that there are certain bits here which have a lot of entropy in them, conditional entropy, and some other bits that have hardly any conditional entropy. That is, they are predictable, completely known there fast. Okay, this is what we want to do. And we needed to now prove that this object actually polarizes. Okay. So let's. So let me state a lemma theorem, which if true will imply whatever we want to. So we define polarizing matrices. I'm going to slightly make it. I'm going to focus on this particular case. So it will be really almost identical to the definition. We'll say that we have epsilon tau polarization. This is the same as polarizing matrix. Basically, if the following happens, so the probability over a random choice of I in n that h of wi condition on w less than I. Previously, we had said it's greater than tau, but I want to be symmetric about this one. So what I'm going to do is so we're going to look at this conditional entropy. Okay. We're going to ask which are going to become extremely which are the hope is some of them become what do we want of it? We want some bits to become extremely unlikely, extremely unpredictable. Therefore, the conditional entropy is close to 1, and some of them to be extremely predictable, so the conditional entropy is close to 0. In other words, what we want to say is hardly anything in the middle. And that's what this is stating, that there's just an epsilon mass in the middle. Among all the coordinates, there's epsilon. Most of the coordinates are either going to go, their conditional entropy is going to become 1 minus tau. They're basically completely unpredictable. They're essentially a random bit. Or they are going less than tau, in which they are completely predictable. But for this one, previously we had talked about less than tau and greater than tau. Here I just want to make, because I want the guys, the ones which are really giving us focus are the ones at the very top, of course. One, so this is the final definition than what I had called polarizing matrix. So let's define object. If the following points. The first thing we say, first will be a simple observation, that is, if you have an epsilon, if we have epsilon tau polarization, implies a linear compression scheme. M being equal to HP plus epsilon plus 2 tau. So these are going to be, this is going to be the M is going to be the target, which is the size of S. And the decompressor D probability that T at Z not equal to C is that's going to be equal to tau times. I want to claim that. So this will be basically there are two things that are coming. Well, what do we need to throw into S? We need to throw the guys in the middle and also the guys in the very top. We need to throw both of them. I want to claim the number of guys in the middle is epsilon n, and I want to claim the number of guys in the top is basically HP plus 2 tau times n, because so that those will be all of the guys. So we'll see the proof of this, but I want to say two things which will complete our and I want to say that the theorem which we will prove is the above matrix, Arikan's matrix. Is for all C, there exists an alpha. So the Arikan's matrix is one. Which one will I put first? 1 by n bar alpha, 1 by n bar C. It's an n by n matrix, and this is what it says. So notice here, the key thing over here is tau. I can make it as small as possible, and that was important for us because error is going to get multiplied by n. So I want tau to be at least significantly. It's not sufficient for it to be small. It has to be smaller than 1 over n. And here this one states that I can get tau to go 1 over n to the C. Epsilon, I don't care. I need it to go to 0. As long as it goes polynomially to 0, that's fine. Therefore, as long as there exists an alpha, that's good enough for me. So we are going to say tau, how would we want? We'll first say how small tau we want to be, as small a polynomial as we want to. That will tell you this would be some inverse polynomial. This could be, correct. This be what we want it to be, like 1 over n to the 1 over n square or 1 over n to the 100, whatever we want. This could be 1 over n to the point not 1, something like that. As long as if the polynomial is sufficient, so it could be 1 over n to the 1000th root or some such thing. That's fine by this. But this tau, so there are two numbers here in polarization. Is both epsilon and tau. Both are going to be small quantities. Both are inverse polynomial. But I want you to understand the fact that one we want it to be really, really small. And the other is as long any inverse polynomial works for us, like 1 over square root 10, 1 over n to the 1 over 100 suffices for epsilon. For tau, it has to be less than 1 over, strictly smaller than 1 over n, so 1 over n square. So let's keep that in mind. So these are the two. I want to claim. So the first, let's do a few things before we plunge into the proof of either one. First, I want to say the implication of this lemma and theorem. What's the consequence of this lemma and theorem? Basically, we have consequence of lemma plus theorem is the fact that what do we get? I want to claim that we have our final result because basically, what's the error? The error which I want, we wanted to get as basically, I want to say, what should I say? What do we want to prove? What do we want to prove? We want to prove this is the thing which we want to do. We want to come up with a compressor. M is at most that much, HP plus epsilon m. Decompressor is this. Furthermore, everything has been stated. N and the running time of decoder should be in poly 1 over epsilon. We saw that the running time of decoder was linear in n. The only thing to check is the n that we get, is it poly in 1 over epsilon? No. The decompressor decoder, which was polynomial. Last time we talked about that.
Now, suppose you want to estimate the the predictable bits are not given to you.
No, S is fixed. S is fixed. S is the one-time thing.
If you are computed,
Yeah,
now you have to decode a predictable bit which is not given in the input.
yeah.
And you are given the previous bits.
Yeah. So how do I do this in polynomial time? So, but one second. How do I do this in poly time? It's not exponential. No, there are only two among the.
So let's say you are decoding the nth bit, which is the most predictable bit,
Yeah.
and you are giving the input value of the first element of some bits.
Yes.
And how do you decide which one is more probable?
So you have to. So what we okay? We didn't do this, but I want to say this is not a. It's not. I don't think it's exponential because what is it? You need to you need to be able to find out the distribution given the first n minus 1 bits. What is the ith bit? As long as you can try the distribution, then you can find out whether 0 is the more probable value 1. And I want to claim for our matrix, this distribution is easy to given our matrix. We know exactly that you have the value for the first I bits. I want to claim what's the distribution you get on the I plus first bit. This is going so this requires some work, but this is it's not an exponential time calculation. The distribution each time you will keep updating the distribution and then basically predict the most probable value among the distribution.
But as they currently increases.
As described currently, but I want to say it's actually fairly simple to make it into this. It's fairly simple. The decoding this one. So actually, the decoding will in fact, I think it's in fact not in it'll just be n log n. The whole in fact, even better than n log n. I believe it's going to be decoding will be in n, poly in n. So our goal will be main thing out here. Technically speaking, I have to do that. I won't have time to do that in this one. There will be things which I'm going to skip even this part of the proof. And what we will now focus is on n. To show why n is polynomial in 1 over epsilon. It's a non-uniform algorithm because S is not this one. So all of this needs to be fixed at the end of the thing. I do not know how much time I have for this one. Yes, so you have to fix. So, but it's currently non-uniform algorithm because S is not good, which I'm not told for every one, S is not good. But there seems to be algorithms which actually give you this also in n log n. In time, and I certainly will not have time to do even S in the lecture. So all of this will come later. So non-uniformity. So notice the decompressor and the compressor needs to know which are the S, which are these heavy unpredictable bits. Question is how do you compute this? So point is it's a one-time thing. Just for every n you need to know this x. Then I can do. Who gives you this S? So and this S does not have, it's not nice enough with the S of the first. It would have been nice with the S of the first. It's scattered across the response. In the case of 2 bits, it was that the first wave was the larger entropy, the second wave was the lower entropy. You want to pick up the top, the high entropy bits, the high condition entropy bits. But it's clear, it's not a priori clear that the top waves will be. The top wave will be. And there is an algorithm which will pick out. It won't pick up, so the algorithm will go a little. If you want it to run, so in nearly linear time, the algorithm actually will not pick the h plus p plus epsilon and become h plus p plus 2 epsilon and take an extra one, but that's okay. Wanted to pick up those sort of things. So that's the non-uniformity. S is so you need to know S. You need to come up with an algorithm. So it's non-uniform in the sense that you fix n. Once somebody gives you S, everything is polynomial after that. The question is who gives you S, and S is given by there's this algorithm with the Tal and Vardy, which gives currently the best algorithm to figure out S for the Arikan's matrix. What else did I want to say? Anything else? I think we are no. So what I want to show now, so there are several things over here. We need to perform theorem. All at this point, I want to say we obtain. The consequence I want to obtain is further. The main consequence of what we have so far is obtain n is poly 1 over epsilon. And why is that? Why is that? Yeah, basically you're going to make the error to be 1 by n power alpha. That is going to be epsilon. Therefore, that's the whole thing. So basically, you're going to set epsilon to be something like 1 by n power alpha, which will mean that n is 1 by epsilon to the power 1 over half, which is poly. That's the only takeaway from this. So n is polynomial. Two further things we need to do. We need to do the decompressor. Compressor, and we also need to find this. And yes, both can be done in poly time, poly 1 over time, not into. So yeah, modulo these three facts, we have our compressor that we want. So I will not focus on the decompressor and S. I will try to give you enough reason to believe why the theorem is true. That also we won't have full time, but let's see how far we can go. Okay. So let's start off with the easier one. Let's start off with the proof of the line. So basically, it says that this is the case. So what should you be doing? It's the most standard thing. You're going to divide the bits into three types of bits. The high entropy bits, those are those I in n, such that HW less than I is greater than 1 minus tau. The low entropy bits, I is less than tau, and the middle bits. Between tau to 1 minus tau. And epsilon tau polarization implies that size of n is less than or equal to epsilon n. That's what most of the guys become extremely predictable or extremely unpredictable. That's what we have. But we also, what are the other facts we have? We have size of h plus size of L plus size of M certainly is n.
Shouldn't that hard one be first? It's
What?
with it.
Huh?
Shouldn't that hard one be square with it?
Which?
Because otherwise you're ignoring the condition of entropy except now.
Yeah. So then what am I want to do next? So what do I want to say? I want to also now put a bound on what we have. I want to put a bound on size of h. So size of h is certainly size of h into 1 minus tau is a lower bound on the total entropy of the n bits, because n could have been epsilon could have been 0 and L could have been nothing. All the tau could have been 0. So it's certainly a lower bound on it. But we know that this is less than or equal to the total thing is at least HP times n. So this in particular implies that mod h is less than or equal to HP n by 1 minus tau.
H prime.
What?
That's it.
Yeah.
The entropy is also H in centimeters.
Okay. Yeah. So this is why Madhu used top and bottom. I don't like the word top and bottom, but P plus one plus 2 tau times n. I'll assume that tau is k less than half. It's going to be much, much smaller than half. Suppose less than half, you have this, and hence this will be less than HP plus 2 tau. And F will be equal to F is H union medium. So size of F will be basically HP plus 2 tau. That would be the one. That's basically the proof of the lemma. And the lemma basically says that you focus on the high and the medium bit, put yes on that. So you are going to get a decompressor, and furthermore, we had this error which says that the conditional entropy is at most tau. Then the algorithm which predicts the most likely guy makes error at most tau. Then you do a union bond. So this will just follow from. So the compressor is basically given by you define as to be this, and compressor is basically the Z mapping to EZ. Okay, so now our goal will be to prove not the lemma, but the theorem, which is main. That's what we want to prove. Okay, so let's sort of see what's going to happen. Let's read for what's the picture we want to prove. We have a bunch of initial bits, a bunch of bits to begin with. These bits are sort of in the first round, they are partitioned into two parts. Like this, and then you get the top part, which is basically the sum of these two, and the bottom part, which is exactly this. That's the first step. That's what happened in the first round of polarization. Now you further partition this into two parts. This into two parts, and you get these. This guy is this. This guy is this. And this keeps on happening. This is the sequence, the way the algorithm proceeds. And what we want to do, so we want to look at this quantity, H of, we're going to pick let's look at a random location, right? Pick a random location, right? A random height. I'm looking at H of Wi, W less than I. And I want to say that this, so let's define the quantity X, right? They want to define one way. This is let's keep this one. For random choice I want to say either this goes all the way to 1 or all the way to 0. Look at this quantity. This will, I mean, you pick the I at random, either it will be very close to 1, very close to 0. That's what we want to show. We want to show the following, we want to show the probability. When you pick an I at random, then HW I, W less than I, belongs to say, let's call it say 1 over n to the 100, 1 minus 1 over n to the 100, is definitely equal to 1 over n to the minus 0.000. This is what we want.
The last term is
So this is the epsilon, and that's the tau. All are inverse polynomial. I'm just stating that this is an inverse polynomial which is larger than n. This is an inverse polynomial. This is smaller than n. This I don't care as long as it's inverse polynomial.
C is 100 and alpha is 1000.
Yeah, C is 100 and alpha is 1 over 1000. Sorry, there is no minus. So actually, let's look at protocol. Yeah. So here we'll follow sort of Arikan's approach. So Arikan is going to sort of define a martingale. So he's going to look at the evolution. So you're going to look, if you want to understand the HWI, W less than or equal to I, eventually becomes A goes close to 1 or close to 0. Notice at the very beginning. So let's what I want to say is let's we have this picture. This is the beginning. So this was Z to begin with. So let's just call it actually Z0. Z0 is defined to be Z, and then it splits. Then there's one step of the thing happens, that's Z1. This is this is the first step. Then you have this. This is Z2 and so on. Eventually, everything becomes it goes all the way to one location each. Let's call that ZT. Notice T is log n. This is exactly per log n steps. So ZT, and that's our W. So what we will ask is, so this is a process. There's a process going on. You're starting with Z0, that it's evolving over these T steps, Z1, Z2, all the way to ZT. We're hoping that initially the first process in Z0, notice the conditional entropy of all, they are all independent bits. All the conditional entropies are HP. What I want to say is, as this process evolves, some of things are going closer to 1, some of things are going closer to 0. So you're going to see this evolution of the conditional entropies as we progress along this axis. So there's no time here, but I'm going to call it sort of the time axis. It's moving along. There's Z0, which is my initial vector. You're mixing it a little bit, mixing it furthermore, and you keep doing this. And what you want to ask is this particular. We're going to choose a random guy, say this location. So let's pick I at random from n and set the random variable xj to be the entropy of zj I given zj less than I. The xj is basically the conditional entropy in the jth phase of this random bit I. The only randomness over here is the I, which index everything. Bernoulli and all have gone out of picture. They are there, but they are all they have all become deterministic only because I'm talking about entropies. The randomness for this process is the choice of the location. So let's keep this definition in our hand. And this object, so let's look at the sequence of random variables. We have x0, x1, all the way up to xt. This sequence of random variables is what now we have called Arikan's martingale. You can see why it's a martingale. What is a martingale? How many of you have done the probability quiz? So suppose you have a process, say we have a process. I used Y naughts, I haven't used capital Y's. So that's called. Let me use X naught, the same guy which I'm going to use. X naught, X1, XT, XT. This is a martingale. Technically, martingales are defined using filtrations and all. I'm not going to, for us, this following definition will suffice. If for all j in 1 to t, and all possible supports a1 to a j minus 1, If the martingales, each of the martingales is in some step, it takes values in some set m. Martingale takes value in some set m. Then expected value of xj given the entire past, that is x0 is a0, x1 is a1, xj minus 1 is aj minus 1. So given the trajectory, the entire trajectory that you have taken so far, I'm asking what's the expected value of xj. This says that independent of what the trajectory is, it's just the fact, what the fact is the last point. It's just ag. This is when I call it a martingale. Ag minus. And what I want to observe is actually, so notice out with x, what is x0 for our case? X0 is just HP. In fact, x0, there is no random variable. So it's not a, for all the whichever choice of it, it's actually the fixed value. There's no randomness in the first case. X0 is for in our setting. It's not that the expectation of x0 is HP, it's actually x0 is HP. It's a deterministic random. Now, I want you to notice how things are evolving. Two guys, you take two guys with some conditional entropies and they are mixing together. But you know that when they mix together, the sum of the two conditional entropies is exactly equal to the sum of these two conditional entropies to begin. That's because you know that the entropy of this system is the same as that entropy because that's a permutation. Therefore, what will happen is expectation on this side will be the same as the expectation. This is just basically that will take all I'm claiming is, suppose you have this system. There was an A here and a B here, which got A plus B and a B. This is some Z in this whole. It could be any particular one Z like this, somewhere out there. So in particular, notice, so let's stare at this a little carefully. What we care is not just to, ideally I would like to come. This is certainly true. HA plus HB, they are independent to begin with. So we know this fact, H of A plus B. Let me write it this way, let me write it a little more. What do we want? H of A comma B certainly is the same as H of A plus B comma B. And this side we have H of A plus B plus H of B given A plus B. This side I'm going to write as H of A plus H of B given A. But H of, to begin with, initially H of B given A was just H of B because they were independent at the very beginning. This is not true for an arbitrary triangle, arbitrary Z in between. But let's stare at this. So at this point, at least, all I want to say, at the very first step, when you move from here to here, the expectation is preserved because of the C. That is the conditional expectation. This is what we wanted to look at. That actually, this was X0. X0s are all the H's. This is the various guys which you are looking at. You actually wanted the whole past, but the only thing, everything else was independent. The only thing that mattered was the guy with which you are paired up with. That's the only thing that's going to cause a issue. That is the guy which you have been paired up with, rather, not the guy you're going to get paired up with. This is the only conditional entropy. Though you had a condition on the entire past, the only thing that will really matter is the guy you have been paired up with. And this tells you that the expectation is maintained. So it's a martingale, at least in the first step, the expectation is maintained. What I want to say, let's look at it a little more carefully. I want to say there's something more happening. So we have this process. Some process like this. And there was a Z happening here. So let's take a particular A here and a B here. What you needed with A was, what you wanted here is A conditioned on its past. But notice its past up to this point, it only depends on this. The other guys have not even entangled with it at this point of time. It's complete. It only depends on things all the way up to here. It's only things in this. Similarly, B will have its own past, x plus y. That is what I mean to say. What I'm not going to. That's what your end. That's at my end. Okay. So what I have to look at is the conditional entropy of A given its entire past. But I'm not going to write the x is not going to talk about the entire past. It's only the past in this particular this one. Where all the things that A has, there's a whole bunch of the past which have not yet mixed with these two things which we don't care about right now. They will cause this one. So the x is only I'm not formally defining it, but it can be formally defined. Whereas B, I have to talk about everything for past for A, past for B. This is the conditional entropy I have to look at. But notice that B is independent of this part here. At this only when this mixing happening, so technically speaking, all I want to say is we would like to compare these objects. We have the initial entropy, initial count is something like h of A given x plus h of B given xy. But I want to claim this is the same as h of A given x. I'm not formally defining this because it's going to be a mess to formally define this. It's just h of B given y. There's the x part here which has not yet in the history of this. This is not that the x part has not yet played a role in these definition. And further note, at this point, Ax and By are identical random variables. Also, that is when at the time of when they are going to get mixed, A and its history, B and its history that depend on it are identical random variables. The mixture happens only when A and B get mixed. So I want to take actually these two are exactly the same. In fact, this is exactly the same quantity being written, right? Stare at this a little much, you can get this. And what will happen and what we want, and the ending sum will be h of what you want is h of A plus B. You want A plus B. And you want the entire history, that is h of A plus B given x. X. B its history will be A plus B. And but it is not x plus y, but it's x comma y. X comma y. We'll have all of this in its. What we want over here is h of A plus B conditioned on x plus h of B conditioned on A plus B x y. And this is actually exactly what we said was the same statement with two h of we have h of A comma B.
Actually, in the block of A, the elements that come after it, shouldn't they come the continuum of B?
They will come, but they don't. They will not interfere. They will not interfere. They will be in the conditional path, but they will not. They are independent. They will. They're all independent. Yeah. So you are claiming. What you're claiming is this guy over here will come in the history of B. But the point is, those guys are not yet mixed. They will be all independent bits. That's why I can only talk x. X roughly is this. X is this guy. And y is just this guy. It didn't matter, the other guys don't matter.
Yes, the elements after him only mix with the elements after.
Yeah, they will mix only much later. Therefore, even though the actual conditional entropies I have to consider that for B, I have to consider X, the part over there, and Y. It doesn't matter, they are independent. So this is the actual file you are. And it's not hard to check that h of AB given this one is exactly equal to h of A plus B, B given xy. So this, the right hand side is exactly h of a plus b given xy and plus h of b given a plus b xy. The left hand side is h of b given h of a given x comma y plus h of b given a comma x comma y. But this is y doesn't matter for a, it's just h of a given x. X and a don't matter for b, this is h of b given y. And because of this, now we have the whole, it sort of opens out and you'll have conditional, and you'll have this property that it will remain a martingale. Basically, you have to make these, you have to formally define what x and y are, but once you write this, you'll see that it's a martingale. That is basically the expectation. If you have a particular value at one place, the next step, because things are only summing up, this condition, because of the chain rule of the way it happens here, things are only summing. This one, the expectation of the next step will be the same as what you saw the previous. That's all I'm saying. So this change is a martingale, but that's not enough for us. What we want is this martingale, which is this guy. So this sequence, this xj is this conditional. Xj is the conditional entropy of a random location at the jth step, and we want this as time progresses to sort of polarize with 0 and 1. It starts off at hp, it's going to keep increasing, decreasing as it goes, but what we want to say, most of the time either it goes to 1 or goes to 0. This is what we want. Particular what we want, let's get what we want, but this the theorem we want to prove. We want to prove what is called strong polarization. We want to prove that, so no, recall that T is log n here. We want to prove that probability that there is an xt, that this lies, what did we say, n to the 100t, 1 to the n to the 100t, that is exactly 2 to the minus 100t and 1 minus 2 to the minus 100t. This is less than or equal to 1 by 2 to the 0.001. 2t has become log n, hence therefore this is what we want. What we want to prove is the following thing. Want to prove So you have, so what's the thing going on? You have a sequence of, it's a martingale, starting off with some value and it's progressing in time. Okay? And you want to say that it eventually goes to the true end. It's always another between 0 and 1, the entropy of the conditional entropy of a bit. It's always when there is between 0 and 1. And you want to say it either goes to 0 or 1. Let's look at some of such processes and see which one of them actually go to 0 or 1. 0 or 1, and see what is the property of such a process that you want to, in order to say that it goes to 0 or 1. So let's see some examples of martingales. Examples of martingales. In which take value in the range 0, 1. So what you could, one simple example is, usually nicest example which we give is you start off with the x0 being half. So let's look at example 1. X0 is half. You start with the midpoint. Then at any xt, you either add half. So x1 is, if you are at half, either you go to 1/4 or you go to 3/4. You go to 1/4 or 3/4. So in general, this one is xt minus 1 plus 1 by, what should it be? T minus 1 or t minus 2? xt minus 1 minus 1 by that should be t minus should be t. What should the number be?
You got T.
2 power t, or in fact t plus 1,
Plus, yeah.
t plus 1, no?
Yeah, T plus. So when T is 0, it should be. So when T is 1, it should be what?
Yeah. This is a martingale because the expectation is maintained. If you're progressing into one, and you can ask what's happening. This is an evolution of a thing. It's starting off with half, going to either 1, 4, 3, 4, then after 1, 4, 3, 4, it's going to go to half 4. Does this? What's the final distribution of this one? Okay. It's uniform. So this is not something which we want. This is not going off to the ends. It's going to give you a tau 1 minus tau. So it's going to be there with probability 1 minus 2 tau. Not going to be there with probability epsilon. So this is not something which is sort of going off to the extreme. And why is that happening? So let's look at this example. We'll see so there's something problematic with this thing. The reason why that's not happening is we'll try to identify what are some problematic features and then say if we don't have those problematic features, it will go off to the ends. So this is one example of one martingale. The other one is the same thing. I'm going to start off with x0 being half. Actually, and then xt. So what will we do is now we'll pick or in fact you can this is more a general version of it. I'm going to choose x0 to be p and xt to be xt minus 1 plus half minimum of xt and 1 minus xt with probability half and xt minus 1 plus half minimum xt 1 minus xt with probability. Sorry, all of these are steaming.
Another is plus half, the other is minus.
Yeah. These are easier said than formally described. So you follow what this is also something that moves. How does this move like? I'm not fully sure what this moves like, but
Always same like the first part.
this is more or less, this is like every step isn't like the uniform distribution. No, it's every step is not the uniform distribution.
To the junction even slower than
The jumps, no, the jumps could be this one. There the jumps are 1 over 2t plus 1. If it's closer, there is a far jump other way also. That is one jump is very small. You go to either that midpoint or you go to this midpoint. Yeah. Okay. Does this polarize?
so by convergence theorem, this martingale must converge somewhere.
Yeah.
Suppose it converges on the interval 0, half.
Why do you know it converges somewhere?
Martingale converges.
No, what do you need? The first one doesn't converge.
No, I mean, I'm saying that the sequence x1 omega, x2 omega, xt omega.
Yeah.
It's converges.
Yeah.
Yeah, each one is converging. Yeah, but
They don't converge to a single number.
yeah, they don't converge. Yeah, each one is converging. Yeah, each one is converging. But I want to show
Which one is smaller? So if it gets closer to one end, it gets smaller and smaller.
yeah, it takes smaller and smaller steps in both directions. It takes smaller steps. And if it's in the middle, it actually takes large steps. So I would say this is actually going to go off to the ends. It looks like it will go off to the ends. So there's yet another thing. So
Actually, yes, this is polarizing because again by the martingale convergence theorem, it must converge to some A. And if this A is bounded either from 0 or 1, and in the next step, it is alpha bounded.
Okay,
That is a contradiction.
once again, come again.
So by martingale convergence theorem, this sequence almost similarly converges to
Yeah.
some A.
No,
Suppose A is not. So yeah, so almost purely.
fair enough, fair enough. Yeah.
Yes.
Yeah.
But the rate.
Yeah. Okay, do you have a pen with you, Sunil? Okay, great, that's this one. So let's do one more thing, which I will not write on the board instead. So this will, it does converge, but it will not come. I'm not sure how fast it comes. What we want is not just go to the ends, we want it to go to the ends in log steps. Okay, these steps. So here, the third one, which I will talk about, is xt plus 1 is xt squared, and it's 2xt minus xt squared. And the way to look at this is the probability half it does this, the probability half it does this. And the way to actually view this is not, if to think, this is think of this as 1 minus xt whole square and 1 minus. That's what it is. So you're at a particular value, it either squares the distance to 0 or squares the distance to 1. That's what. The next thing is the one of these. That's how it is progress. So either the distance to 0 or the distance to 1 is reduces by a square factor each time. This actually, so I think the previous one does not. The previous one polarizes, but not polarizes fast enough. The first one doesn't polarize at all. The second one polarizes, but does not polarize fast enough. This one actually polarizes and actually polarizes fast enough. In fact, this was the original proof. The original proof of Arikan's martingale converges fast showed that they actually satisfy this problem. This is not what we will do. This is not what we will do. What we will do. So what the quick thing is xt plus 1 is equal to, if here xt could be any number, out of it x0 being alpha, and xt plus 1 is xt squared with probability half and 2xt minus xt squared with probability half. So what I want to say is there's some feature, I want to identify some property which I think is essential for a thing to polarize. Firstly, why did the first guy not polarize? Eventually, the step sizes became very, very small. What we want, we don't want this to be the case. The second one, polarize, is probably not fast enough because once it's in the middle, I want to take large steps out. So the first thing is, this is a very local phenomenon, we call it local polarization. Local polarization, you'll say x0, x1, x2 in the martingale. Satisfies local polarization. So the following properties. One is there must be variance in the middle. In the middle, if you look at the steps, the variance should not go to 0 in the middle. That is, if you are currently in the middle, not at the very end, the step sizes should be large, is what I want to say. So basically, what I want to say is, if you are in the middle, how middle, that I will talk of it as tau. So basically, what you want to say is, you want to look at the variance of xt conditioned on xt minus 1 belongs to tau 1 minus tau. So it's in the middle. It's not yet gone to the ends. I'm looking at the middle. This should be at least sigma square. But basically, for all tau, they must exist as sigma. I tell you what I consider the middle, then you must tell me that there is a variance, so that there is always so much step going away. This doesn't go to the. This is not. Notice most importantly, this is a number independent of t. For all t, this happens. So look, the first martingale was a bad thing because the variance kept shrinking with t. This states that no matter what t is, if you are in the middle, you will take huge steps to either end. This is what is happening over there. So you don't, so one property which we would want to show fast convergence is whenever you are in the middle, you just take big steps, either up or and all the martingales don't have to be this. That is given a particular point, they need to just take two values, but the martingales we consider will all be these two values. We just split off into two values. The next step will be probability over two potential values. That's all. It's that is each time what I claim is from given a particular thing, given a xt minus 1, there are only two values equally likely at the next. That's all martingales we are considering about that type. But a martingale does not have to be that. So what I'm saying is, those will be what we call simple martingales, but I don't think I have time to go into that part of the super talk. What I'm saying is, this is what I call variance. This is what I call variance in the middle. Okay. Other thing I want, okay, that's variance in the middle. That says when you are in the middle, you take big steps. Other one is we want suction at the ends. At the end, once you go to the ends, you really begin going much. Once you go to the end, you begin going very fast to the extreme end. So what I want is what I call suction at the ends. Because for all C, C is going to basically what you want is the following. The same thing will let's talk about the zero end. The same thing I can write it for the one end also, zero end. The condition on the fact that xt minus 1 is less than tau. So it's already at the end. What I want is xt should fall by factor c. That is for all c greater than 1, there must exist a tau such that for all t, the following happens. This must happen with significant probability.
In this case, it's the probability that is 0.
Which case?
In our
second example, this is not true. I don't get this for every c.
no, in Arikan martingale.
Huh?
In Arikan martingale, if it's non-zero, it's half.
If it's non-zero, it's half. If it's non-zero, it's half. Yeah. If it's non-zero, it's half. So yeah. So one half. Yeah. If it's non-zero, it's half. But this is what I want of it. That is when it shrinks, when it goes to the end, it really goes. This is the zero end. The same thing is exactly true. You have to write the symmetric thing for the one end, which is the probability that if what should it be there? 1 minus xt minus 1 is less than tau. Then 1 minus xt should be less than 1 minus xt minus 1 by c. That should be given. Yeah. And the reason we want this is once we go to the end, we go super fast. This is not true for our second martingale. Our second martingale does not, it goes to the end, but it does once it goes to the end, it doesn't have suction, it doesn't just absorb itself to the extreme to 0 and 1 so far. It only halves the gap each time. Whereas here I tell you, I give you a C, and based on that C, you must be able to say you can go as fast to 1. This C is not my choice. This is of course a definition. And the thing to notice is martingale, the first example doesn't satisfy variance in the middle. The second example doesn't satisfy suction at the ends. It satisfies variance in the middle, but doesn't satisfy suction at the ends. And basically, this proves that this is different from this martingale will satisfy both the properties. This actually will notice that this will have the suction at the end, because once you're small, you're going to become really, you're squaring the gap. You're going to become really, really small. This will have this property. So the original proof of Arikan actually showed that what they would show was the way the earlier proofs of prior to the Blasek proof which we are doing would show that given the Arikan martingale, it's you bound each step by another super martingale, which will be this, which will satisfy this property, and this one they will show goes to the ends. What we will do is we directly go to the Arikan's martingale, and I think basically there will be two theorems which we need to show. That is, one is Arikan's martingale satisfies local polarization. The reason I'm calling this local is this is the condition over here is something about what's happening from one step to the next step. It's not a global step. I'm not asking you something about xt to this one. What about xt given xt minus 1 behaves a particular? That's why it's called a local. It's a local. Well, this property is a local phenomenon. And the first thing to observe will be that Arikan's martingale actually satisfies local polarization. I will not do this. This is just take the entropy function, open it out, and just calculus with this. Take the entropy function and observe that all these things are satisfied. These are just basically calculus. You just observe the entropy function for please satisfy this program. We will skip this proof. I don't know any cleaner way of proving this other than just expanding out the respective entropies and noticing that these things are true. Observe that then let's the conditional entropy at one point be HP0 and HP1. What happens when you mix it, you find it out and then say what will happen. So this one it will not do it's calculus involving entropy function and basically approximations of it using Taylor and Taylor approximations. Skip. Next theorem will be that local polarization implies strong polarization. So just recall what strong polarization is. In strong polarization, we want to prove probability that xt lies in due to minus 100t due to 1 minus 100t. This is going to be equal to 1 by 2 to the point not 1. This is what strong polarization is. You need to prove this. The actual theorem will be obtained by these two. Probably the high level sketch of the proof sketch of local implies strong. Okay, so we have a martingale which has this property. It's a simple, it's a further simple martingale. What I mean by simple martingale is given a particular value, the next value is one or two possible values, half each. That's how it's evolving in time. It has variance in the middle. Whenever the martingale thing is in the middle, it takes few steps. One closer to 0, one closer to 1. So you tell me what is middle, you tell me what is tau, that determines the middle. I tell you for that tau, there is a sufficient variance. So the closer tau is to 0, the variance might become smaller and smaller. But you tell me what is the middle. If the middle is very, very small, then the huge steps. So that's what the first thing the variance in the middle. The second one is stating that once you go to function, once you go close to the ends, then you go rapidly close to the extreme ends. That is once for you want to, you are asking, and here the order of quantifiers is not tau, it's not telling you what the end is. I think we are asking how rapid you want it to go. That is by C, that's the factor C. This is what is going to help us with the strong convergence. From fast convergence, I'm going to tell you how fast I want to converge. Then you tell me what is then what do you mean by the end? So if you're as so close to the end, then each step is at least probability half, you're going to become factor C even closer to B. That's what fraction of the ends is going to tell you. Based on this, we want to show that you have strong polarization. And the proof of this, so actually it's a clever potential. So let's start off with it's a clever potential function argument. If you go into why they chose this potential function, but it'll take me a little time, so let's start off with, let's see why, given the potential function, so let's define this potential function for square root x, square root 1 minus x. It's basically the distance. And it's clear that you have to use xt and 1 minus xt. These are the distances from the two ends, and this is something that we want to minimize the potential. We want to have some function, and basically the distance to the end, and we want to show that this decreases. So this is the distance to the two ends. Ideally, I would like to work with xt and 1 minus xt. That doesn't work. And so they go for other things, and square root is chosen because convexity works in that direction and not xt square and 1 minus xt square. You will somewhere their proof will need Jensen. So that's the reason why they go for this convex function. And the claim, which is not hard to see, this uses both variants in the middle and this one, is there exists a beta less than 1 such that the expected value of Vt conditioned on xt minus 1. So given what you know in the past, this always shrinks by a factor. It is this, you can show that variance in the middle and fraction at the end tells you that this xt is shrinks by a factor of beta. Beta is some number less than 1, the fixed constant less than 1, independent of t, it shrinks by 2. So this is not actually, this is the square root of one. This yeah. So it's not Euclidean distance. There's a square root sitting there. Yeah. So this guy reduces by factor beta, and the proof of this uses both variance in the middle and suction attributes. Okay. Once again, I'll skip the proof of this. But I want to say that once we have this, we have something quite this one. What do we have? We have that the expected value of Vt. So each time this is reducing by a factor beta. So therefore, this is certainly less than beta to the power t. It's gone down after t steps, it's gone down dramatically. But now you have a very simple statement. Now you have a probability that Pt is larger than, say, beta to the t by 2 is less than or equal to beta to the t by 2. So it's just Markov.
Minus beta minus t.
Beta is a number less than 1. Beta is a number less than 1. This is just Markov Arikan. But then you are more or less what's this stating? This is stating that probability, this is by Markov. Probability that the min of square root xt, so the square root I take it to the other side, the min of xt and 1 minus xt is greater than or equal to beta to the t is less than or equal to beta to the t by 2. That is equivalently probability that xt lies in beta t or 1 minus beta t is less than or equal to beta to the t by 2. So beta is some number. Think of beta as some number close to 0.99999 or something. So what does this give you? Think of beta as say 2 it's some arbitrary number. I don't have control on that number. So I basically get beta could be very small. Beta could be very small, beta could be very large. What is
Very close to 1.
very close to 1. Very close to 1. So it's something like 2 minus 0.0001 times t. Beta itself is beta could be any number. Say beta is very close to 1, but it's less than 1. So say beta is some 2 point minus point not 1. So it's something very close to 1. Because I put the minus sign. So this is what we are getting. Okay, this point not 1 is different from this because there's a by 2 difference. This is actually point not 5. Make sure 0. So what do we have? Notice that this part of it, this part is good. This is what we wanted. The epsilon, we wanted some polynomial to party. This is not good enough. We wanted it to be we wanted to have this not to be 0.001, we want it to be like 100t. We wanted it because we want that polynomial to be less than n. So this is not good enough. Huh? Yeah, that's it. Everything over here is so this is not good enough. This is good. So they managed to get polarization in which epsilon is so small. So epsilon and tau both are now going to 0 for us. Epsilon is polynomially small. Tau is also polynomially small, but we want to be able to control the exponent, and that's not happened here. The exponent is not our. This analysis doesn't give an exponent of our choice. It gives you some exponent, so it's not necessarily an exponent of it. For epsilon, that was okay for us. For tau, that's not okay. So we need to do something more to show that it goes. Is this fine so far? So assuming that claim is once again, that claim is an easy thing from Jensen and the properties of local polarization. So now what I want to say is, okay, so now we split it. So this is not good enough. This is not good enough. So now we split the convergence group into 2 phases. First P by 2 phase, we say we will get this. So we have to do in T phase, T run, time is progressing. By T, you want to say you have strong polarization. We'll do the first T by 2 and we'll get this at the end. So the first T by 2, we got sort of polarization, which is sort of not as strong polarization as one, but not. So let's call this semi-strong polarization. So at this point, what has happened? We have a random variable. This is 1 and 0. You know, it's almost never in this one. It's gone. It's completely sitting here. It's completely sitting here. Except that I don't get to this region. I want to make it even smaller. It's polynomially small right now, but I want to be able to control how small the polynomial is. This is where but now we have suction again. Suction at the end is a very strong property. It says, if it goes to a particular thing, then it's going to shrink like by a factor of C, and we get to control the factor of C. So you could use the first feedback. So the actual analysis will go into 2 phases. 2 phases. First, T by 2 phases obtain semi-strong polarization. The next T by 2 phases, I want to say I'm going to invariably keep dropping by a factor C each time, or at least most of the times, the probably half over drop by a factor C. So you're going to notice you're either dropping by a factor C, otherwise you're at most doubling. The quantity is either dropping by C, but you know the expectation of the quantity, expectation of the 2 values is this. Therefore, the other quantity can't be too much larger than what you are currently. At best, at worst, double the current quantity. So probably at most half you are doubling. So probably at least half you are dropping by a factor C. So if you run this for several times, you know that you are going to see a lot of C's. You're going to see at least say 2/3 times you are going to say drop by a factor C, and that's good enough to that will shrink. So you're at some exponential, it's going to shrink it very, very fast. But this is true only if you're always at the end. Suppose at some point of time it moves off the end, you don't have suction at end. Suction at end is promised only if you are within a particular top. So you're having so right now this is this 2 power minus 0.001 t. You know, that's that there, and you're going to keep making steps there. What I want to claim, you can make this formal. What I want to say is the following thing. See, this is a martingale. So let's forget about the martingale at the bottom. You've already gone there. You have martingale there. As long as you know that the martingale is below some threshold tau, we get to choose this. So I want to. So how does the suction at end go? Suction at end goes. You drop by a factor of C. So if you want to drop by a factor of C, there is a tau that as long as you're less than this tau, you will drop by a factor C. Now you need to make sure that this guy, this martingale that's walking over here, never crosses this over here. If it crosses this, you're in for trouble. Otherwise, you know you're going to at least 2/3 with high probability. Charnavon will tell you 2/3 of the T by 2 steps you will drop by a factor C, and that is really going to shrink you like anything. Yeah, that's exactly what we'll say. But we still need the fact that it never crosses this. It never crosses this tau. The conditional on the fact that it never crosses that tau. It never crosses this guy. This xt is going to shrink by a factor C most of the time. Therefore, 2/3 of the time it's going 1/3 of the time possibly it's shrinking by a factor C. 2/3 of the time it's doubling. But C is a number at our control. Therefore, we can just think it, which is the same thing as stating that log xt is biased will going close to 0 as. But this is only assuming that it never crosses tau. But then, so I want to ask, what is the process? So is it on my end or?
Okay, so now we have a biased random walk with two absorbing barriers and with high probability to use the left barrier.
Condition on the fact that it doesn't cross.
So I'd say one of the absorbing barriers is the threshold tau.
Yeah, but why is it an absorbing
No,
barrier?
I'm saying maybe it is that I am in barrier.
Yeah, but what's the probability of reaching?
Okay, so you have a biased random walk.
Yes.
With two barriers in there.
Yeah.
Then you lower minimum probability if you hit the left barrier if you biased to the left.
Yes. That's all. But but you need to ask the probability, what is the probability that you hit tau? That if anywhere in this walk that you remain less than tau.
Yes, so there is one barrier is at tau.
Yeah.
And the other barrier is at it's tau. Sorry, one barrier is at the tau given as the middle.
Okay.
And the other barrier is at 2 power minus 0.999 t.
Okay.
Then I will say that since log xt behaves like a biased random walk which moves to the left with more bias than to the right.
Yeah.
Then only hit the left barrier before the right barrier.
That's all the right. You can, yeah.
Yes,
You can do that. You can do that. The way they do it is the following way. The way they do it is they ask what is the probability that the martingale ever crosses the threshold tau. And this you can show by doing this one that what's the probability of the martingale? You know that it is already at 2 to the minus 0.001 t. What's the probability that it crosses tau? It will be at most to the minus 0.001 t by tau. So that's the problem. But now to eliminate that probability, that's the error probability. But for that, you are in a thing which is going to shrink with probability C each time. will see 1/3 of the time, and at most 2/3 of the time it's going to double. So this is enough to train. So put these together. So the next 3/2 cases, all I want to say is with probability beta t/2 by tau, the martingale never crosses tau. But in this case, it shrinks by factor C at least half the time. And doubles most half the time.
Actually, exactly how.
Yeah, exactly half. Yeah. Yeah, our martingale is exactly half. Anything that local polarization, because I put a data equal to half, that's all right. Yeah. Our martingale is exactly, both of them are exactly. And hence you get this. So then it will shrink. So the error probability will just be beta. So basically the tau, which was previously beta t/2, that will go into the error probability, and this you have a new tau, which is really small anti-error control. You have to do the calculation. I'm not going to do them, but you can make all of this. This is there, and in the book they have done all of this. They done it all very detailed. Notation is very heavy, but basically the idea is this. Okay, so what we will do next is this will be the end of follow-up course. We will enter a new topic called multiplicity code starting next lecture, and we'll do it to understand multiplicity code and to various applications. To exist questions will be still left unanswered in coding theory. We want to ask code which list decoding of the capacity. For instance, we want to get good locally decodable codes with rate close to 1. That's a problem which we didn't answer. And other questions and other connections to complexity. And we'll see all of them through the lens of multiplicity code. That will be all the remaining lectures. The next 4 lectures till end of November. Our last lecture will be in November. We won't have any lectures in December. December will be for the presentations. And the second week of December, just before you guys leave for FST, will be the final exam for those who are taking the final exam. Okay.
So question related to a previous,
Yeah.
given an English code, is there what is the base alphabet size of it?
So
Each code actually alphabet is equal to probably.
So you can show that it has been omega k, the alphabet. What a reads out in base omega n, that's open actually, where it is between k and m.
This alphabet says for English.
We don't know. So I think the best thing this is open, that is, we have to, in the case if k and n are comparable, then this is one. Yeah, but the different k and n, I think we haven't yet printed it. So in case very small compared to n, question is, can you come up with a MDS code whose alphabet is smaller than n? It's conceivable, we don't know. I think this is the state of the project.
So, but the other existing these codes we can have it bigger than this.
They could be MDS code, but we don't know. The best for MDS code, the best that we know is the reason. Yeah.
So, from which we have found that double why cannot grow the expectation is.
The expectation is the right. So, and take only one or two values. So one falls by a factor of 3. The other one cannot.
2 minus 1 by 3.
2 minus 1 by 3 is what it can be. That's